Hello, Assalamualaikum. Good morning. So this is a lecture on free vibration of a single degree of freedom system, where now we are talking about damped free vibration. So now we have a model like this. Basically, you have K, you have C, okay, and your mass, okay, with no input, okay, but you have an output of xt or response of xt. So this is a depiction of a free vibration of a single degree of freedom system where you only have one mass and there is no force coming into the system. All right, so based on this lecture, you should be able to, quite similarly in the previous lecture, you should be able to determine the equation of motion, looking at different types of damped single degree of freedom system, which consists of undamped, critically damped, overdamped, solve the EOM, and also determine the damped natural frequency of an underdamped single degree of freedom system, and also looking into how you can actually calculate damping ratio, because now it's a damped system, so you have more parameters that you need to solve. So these are some of the things that we hope you can calculate. Alright, so the analysis of undamped free vibrations is only an idealization, so it doesn't occur because in our real world there are a lot of loss or frictions. So in this case, that's why an undamped free vibration is only an ideal case where it does not account for energy loss to friction. So once set into motion, such idealized system vibrate forever with a constant amplitude. However, in real system, it will stop, isn't it? If you actually have a mass hanging on a spring like this, you know, it will eventually stop if you try to vibrate it up and down. It will eventually stop because there is friction, such as from the air. So when the amount of energy loss in the system is small, the results of undamped free vibrations are often good agreement with the real system. But if it's then it's okay to assume undamped. But if it's big, then you will need to consider damped. So common types of friction forces that can remove mechanical energy from vibrating systems include fluid friction, dry friction, internal friction, which arises from solid body when it is deformed. Okay, damping caused by fluid friction is quite common in engineering work, and only linear viscous damping is considered in this lecture. So most of the time we are looking into viscous damping force, linear. So that's why in this class we are focusing on the linear force damping, which is F equals to C x dot, where your C is called the coefficient of the viscous damping, and the unit is Newton second per meter. Okay, the direction of the viscous damping force is always opposite to the direction of the velocity. So let us take a look at this figure. If you remember the steps that in the previous lecture, how we actually define our EOM. How do we write our EOM? So basically, as you can see, the first step is you actually write the force on the of your elements. Okay, so write force on the elements. So here you have two forces, the C and the K. Okay, the C and the K. So you have these two K and C, so you have to draw the free body diagram is basically you have your C and the K in the same direction as your X dot, so you would have like this from your K. So you have KX and CX dot, and then only you draw action reaction of your forces on the mass. Okay, so then you write your EOM based on the mass. So here you have mx double dot equals to summation of forces, which is your CX dot and KX dot, basically oppose the in the opposite direction of your X. So you have negative CX dot and negative KX. So that's how you will get your mx double dot plus kx plus cx dot equals to 0. Okay, or maybe I do it conventional way. You would write your cx dot first plus kx equals to 0. So you would have your equation here. Basically, you would have your equation here in the to relate with this figure. Okay. So then we take a look at so this is how you have it. So you can see that the above equation you have second order ODE basically with constant coefficients. So if you actually write the equation of motion, so if you want to write in terms of exponential function, so why you want to use this exponential function? So you assume xt equals to ae lambda t, because it's easy for you to cancel out. Okay, so then you take x dot. So basically there you have your xt. Sorry, let me just erase this a little bit. So you have your x dot will become lambda a e to the lambda t, and you have your x double dot is equals to, so you put your lambda again, but you have to square because you have the lambda from here. So you have a e to the lambda t, sorry. AE to the lambda t. Okay, so what you do is you substitute into the equation. So remember the equation is you have your okay, if you look at this part here, okay, if you remember your equation is mx double dot plus kx plus cx dot equals to 0. So you substitute your mx double dot will become, okay, if I show this, move this a little bit, okay, over here. So your mx double dot will become your m lambda square ae lambda t plus k lambda kx is a e lambda t plus c, x dot will become your lambda ae. So you can see all would have the same term, isn't it? You have this ae, isn't it? You have all this ae term there. So you can actually bring you can put all the terms together, so it will become ae to the lambda t. Okay, then you would have m lambda square plus c lambda plus k equals to 0. So you can actually 0 divided by this, you bring it to the other side, so you can actually cancel it out, because 0 divided by something is equals to 0. So you would have basically this equation here. Okay, so then you have your, if you look at this, if you look at this, this is actually what we call the characteristic equation. If you remember the equation for characteristic equation, you can solve for the roots, lambda 1 and 2, and you can substitute into the equation. This is actually negative b plus b square. You know, if you remember the equation, basically negative b plus minus b square minus 4ac. To solve for your divided by 2a, to solve for your quadratic equation, yeah, or the characteristic equation. So from there you can solve for your lambda, and you can get the constants from the initial conditions. Quite similarly what we did in our previous lecture, where if you have initial conditions, you can actually solve for some of the constants here, yeah. And the roots can be written in terms of non-dimensional parameter, which is zeta, or what we call the damping ratio. So this is the damping ratio. So basically it is defined as a function of your c, okay, which is your damping constant, your m and your k. So in terms of damping ratio and the natural frequency omega n, the roots of characteristics equation is will become given by this equation. The behavior of the system depends on whether the quantity under the radical is positive, 0, or negative. So you can also see that C that makes the radical 0 is called the critical damping coefficient. So now you have we introduce another term, what we call CC, or critical damping coefficient. So CC is 2m omega n. So in the test, so don't worry, the list of equations will be given. You can also see in the Moodle the list of equations that we will give it to you. But of course you need to know what is C, what is CC. Yeah. The solution, we have 3 distinct types of behavior depending on whether the actual system is damping or greater or equal or less than CC. So those are the characteristics where you have 3 different types. So this is where it comes depending on C is greater, whether it's greater or not from CC. So basically if you have damping is greater than 1, so then the radical is real. So that's why we call overdamp. So you have this solution. So in the list of equations, we'll give it to you where the case of if you have damping is greater than 1, then you would have different equations that you need to use for the solution xt. Okay, if you have equals to 1, okay, where your zeta is equals to 1, then you would have a different equation, Okay, given an initial condition values, you can actually calculate the equation from the equation. So this is the solution. Okay, so this is what we call the critically damped system. So more than one is overdamped, equals to 1 is critically damped. Okay, so this is the comparison. What happens if it's equals to 1? So you can see that in black, okay, this one is equals to 1, which is a critically damped system. So this one is over 1, which is over damped system. So you can see that the displacement simply decreases to 0 as t increases, and the motion is non-vibratory. So quantitatively, the motion for critical damp is the same as the motion for overdamp. Okay, maybe it's not very interesting if you have a problem of overdamp and critically damp, because you cannot see the vibration at all because it's non-vibratory. Okay, but this is why is it important to know the critical damping is especially important, because it is dividing point between non-vibratory motions and damped oscillatory motions. So that's why in this case zeta equals to 1 or critical damp is the dividing of the two conditions. A critically damped system will come to rest in less time than any other system, starting from the same initial conditions, which is the value of damping that provides the fastest return to 0 without oscillation. So this is the third case, however, which is more interesting, where your damping ratio is less than 1, okay, or C is less than CC. So this is what we call the underdamped system, which is quite commonly that we ask you to solve for, because you have it is a system where it has vibration, and you can find a lot of parameters from the graph. Okay, so if you have underdamped system, we introduced to you a new term. Okay, previously we only know about omega n, but now there is a new omega, what we call the damped natural frequency, circular frequency, okay, which is omega d, because you have zeta. So that's why if you look at this equation, if your zeta is equal to 0, then your omega d equals to omega n, basically, isn't it? Okay, sorry, it's okay. So basically, when zeta equals 0 for undamped, which is in the previous lecture, so basically you do not have omega d per se, because your omega d is actually your omega n, because there is no damping. So you have this solution. So if you remember in the previous solution, if you have an exponential function, then you do not have omega d, because omega d is equals to omega n. Okay, so by making use of Euler's formula, you can actually derive the equation, and with the initial conditions, you can actually solve for your solution xt just now, where you can find your a and also your phi. Okay, so you can substitute back into the original formula xt. So you can substitute your a, you have your omega n, so you can substitute all the values and your phi. So using the initial value of a and phi, using initial conditions, you can find a and phi. So if you actually look at the plots for this kind of system, if you actually go into the lab, this is how we characterize the system for underdamped system. So this is how it looks like, where you have, if you look at here, this envelope is what we call, you can see here, it's an exponential function, AE minus zeta omega nt. So it decreases because the exponent is negative. So you have these two envelopes here. So this is where you can actually find what is the value of those functions, and you can determine what is your zeta, basically. And we define as if you have a peak, x1 and x2 here. So you can actually find how does it actually reduce the peak, and the equation that we use is what we call the logarithmic decrement. The tau now, okay, because it's an underdamped system, so the tau now is defined as tau d. So tau d is the damped period of oscillation. Okay, so when you have the damp here, this is another important thing. When you have underdamped, where your zeta is in between 0 to 1, then the damped natural frequency omega d will always be less than the undamped natural frequency of the system. Okay, you can also find the relationship between frequency Fd. Okay, so normally the unit is in hertz, and your tau d, which is period of oscillation, is in seconds. So now instead of using just omega n, you have the term omega d. So previously it was omega n. So now we are using omega d. So let's take a look at example. So you have example 1. You have the torsional pendulum, which has a natural frequency. So as usual, we make sure that you write down what are the values given. So in this case, a torsional pendulum has a natural frequency of 200 cycles per minute when vibrating in vacuum. So there's a clue there. There are two types of natural frequency. Okay, you have 200, and when it is immersed in oil, its natural frequency is found to be 180 cycles per minute. So in this case, we assume the one that is immersed in oil is your omega d. So this one, in terms of cycle per minute, so you have to get your in vacuum, which is omega n. Okay, you have to convert it into radian per second. So you have 2 pi f. Your f is you have your 200 cycles per minute. So basically, in other words, you have 2 pi times your 200 over 60, because minutes, and this one is cycles per minute in order to get your radian per second. So this one is in terms of radian per second. And then another one is actually your omega d. So 180 cycles per minute is your omega d, which you can actually find with 2 pi times 180 over 60. So this one is also in radian per second. You're going to see the values after this. I just make a note there. And you also have mass moment of inertia of the disk, which is actually your J. Okay, your J is equals to 0.2. If you are not sure, maybe you can take a look at the units that they use, mass moment of inertia of the disk. Okay. You want to determine the damping constant. So what you want to find is your damping constant C. If the disk when placed in oil, give an initial. So given another, the next type of question, given initial displacement, which is theta naught is equals to 2 degrees. So you may need to convert it into radian. Yeah, in radian. So find its displacement at the end of the first cycle. So basically, after you find this, you have to find these are kind of steps basically. The second one, you want to find displacement at the end of the first cycle. So remember, this is a rotational system. It's not a linear system. So if it's a linear system, the response is, or displacement is actually x. For rotational system, the displacement is actually theta. So what they want to find is theta at the end of the first cycle. Okay, theta at the end of the first cycle. So first cycle is after one period. Yeah. So there are two parts that you need to solve. So if you look at the solutions, we have it in terms of radian per second. And then once you have your omega d, so it's easy for you to find the damping ratio. So if you look at your damping ratio, you can see that it is less than 1. Yeah? So you can calculate the torsional damping coefficient. So how do we actually get this equation? If you remember, we have it in the previous slide. We have this equation. C is equals to 2m omega n zeta. So if it's torsional, then you would use, instead of m, you use j naught. So that's how you do it. So you have j naught is given. You have got the value of omega n, the zeta. You calculate the zeta, then you can get the torsional damping coefficient. So remember, that's what you want to find out. So maybe I use a CT there. Yeah. So that's how you get your CT. So then you are given initial condition. Remember, I told you you have to convert into radian. Okay, because the standard unit, yeah, this is the standard unit for angle. Okay, for initial condition or displacement in rotational system is theta. So the damped natural period is given by 2 pi over omega d, because you already have omega d value, so you can calculate your tau d. So once you have your all the values here, you have your the CT and so on. Remember, so you can actually calculate your capital pi. So here, when they say find its displacement at the end of the first cycle, so before you want to you have your theta. Basically, you want to find theta. So before you find theta, you can see that your theta is in terms of phi, e negative zeta omega n sine t and so on. So from here, you have to find this first. Okay, just now we have the value of zeta. All this you already have it, but you need to find your capital phi and your angle. So that's what you are doing it here. How do we get this equation? So if you look at your list of equations, okay, you can actually find this equation under underdamped condition. Why is it underdamped? Okay, because your zeta is less than 1. So under underdamped, you have you can use this equation. Okay, let me show you how do we get this equation. So you look at here. Okay, so this is the A value. So basically you have this equation, slide 18. So in the example, this will become your theta t. So that's what you want to find in the example. So you have to find A. So A, in the example, your A is your capital theta. Your phi is your phi. So basically from slide 18 and 19. So how do you actually solve that problem? So this one, see slide 19. Where your this one was A, this one was your V, which is x dot naught, okay, and this one was your x naught. Okay, you have to see slide 19. So basically you need to be able to convert from linear system to a rotational system. Then the rest will be the same. Okay, This one is also from slide 19. See? Slide 19. Okay, maybe I show it again. So you can see that the angle phi, okay, is the same equation. Okay. So that's how you solve the problem. You can see. Okay, the main difference is this one was your V naught or X dot naught. Yeah. The rest are the same. So see slide 19. So from there, once you get your capital pi is the amplitude, and your phi, then you can substitute into the equation. So all the values are there. So you can get your theta t. Okay. So we've done with example 1. Then we can go to the logarithmic decrement. So what it means by logarithmic decrement, basically you want to be able to use this equation. Okay, so if you look at this equation, is what we call the logarithmic decrement delta. This small delta is defined as the natural logarithm of two successive amplitudes. So you can see here is you have xt and xt plus tau d. So let us take a look so that we can understand. Because if you remember the figure just now, it relates to how much it's being decreased. So that's why we call logarithmic decrement. So based on this expression, okay, you can actually calculate your tau when you have omega d tau d equals to 2 pi, then the expression reduces to this relationship. So circular damped natural frequency is substituted into the above equation, then you can get this relationship. But don't worry, okay, the main thing is you are also given in this form in the list of equation, where you can simplify the calculations if you are given in terms of delta. Okay, so what is delta? Okay, you can see here the delta or the logarithmic decrement relationship. So from here, once you get your delta, you can get your zeta. So basically, logarithmic decrement in short is how you can determine your damping ratio, zeta. Okay. So if you look at this relationship, this is the general equation. If you have a peak x1 and a peak x2, is basically ln x1 over x2. So take a look at this figure. So it's quite similar figure in the previous one of the previous slides just now. You can see that you have here x1 and x2. So basically this peak here and this peak here. So this is x1, this is x2. Okay, so if you actually look at this height, you can calculate the logarithmic decrement delta, this small delta, by this equation, where m is an integer which corresponds to the number of complete cycles. So for example, if I give you x1, let's say x1 is 10, x2 is 5, so the delta is equals to, okay, what is x1 to x2? How many cycles is it? It's only one cycle, isn't it? From here to here. So m is equals to 1. Okay, number of complete cycle. So it's just 1 ln 10. X1 is 10 over 5. Okay, so what it means by here is m. So if m equals to 1, so m plus 1 is equals to 2. It's just saying that 1 over 1 ln x1 over x2. Okay, so that is easy, isn't it? So if I say, let's say the second cycle, the value is 3. So how many cycles I have here? From 10 to 3. I have m equals to 2. Alright, so let's say I erase this. So now from 10 to 3, you have 1 cycle, 2 cycle, isn't it? So from there, so let me just change the value, the color. So from here to here, my m equals to 2. So in this case, my delta is equals to 1 over 2. So you take a look at x1 and not x2 but x3, because now your m plus 1, it should be 2 plus 1, which is x3. So it should be ln x1 over x3. So which is equals to 1 over 2. x1 is 10 and x3 is, this is 1, 2, 3. x3 is 3. So you can calculate what is your delta. So make sure you know the number of cycles is less 1 than the number of peaks. In this case, you have 3 peaks, but the cycle is 2. So that's what it says by this relationship. Okay. So this is the case where you have zeta is less or equals to 0.3, or your delta is less than or equals to 2. So you can have the luxury of using this equation. So that be a easier sample. Yeah. So in example 2, you have free vibration response, electric motor weight 500 Newton. You mounted on a flexible foundation. So you want to find the undamped and damped natural frequency. So take a look at this figure. So you can get some information there. So they want to find the undamped and damped natural frequency of the system. So from this figure, you can see these are all the values of x1, okay, x2, x3. So you can also see that the period, so you can take from this point to this point, which is basically the cycle. Sorry. Let me just so if you take a look at the peak to peak. So basically when we measure the period peak to peak, like this one, is actually 0.2. So tau d is equals to 0.2. So if you take a look at this problem, so from the time response, the damped natural period is 0.2. So you can calculate your omega d. You can also calculate your logarithmic decrement. So in this case, they are using 3 cycles. So normally we take the highest value that we have, highest number of cycles that we have. So you can see here to here is 1 cycle, because you have 4 peaks. So here to here you have 2, here to here you have 3. So you have 3 cycles. So basically you have 3 cycles and 4 peaks. You have x4 here. So that's why when you calculate, you are using 1 over 3 cycles and the highest peak with the lowest peak, which is this one is x1, this one is x4. Okay, then you can get the value. If you have a delta, since your delta is less than 2, so you can use this simplified equation, and you can also calculate your undamped natural period. Okay, then you have your, you can calculate your spring constant of the foundation, because you already have your m given. So take note that I forgot to tell you, this one, okay, the motor weight, they already given it in Newton. So that's why for your mass you have to divide with g. So basically in this case you have your weight, okay, in Newton, you have to divide by your g. So because weight equals to mg. So you get your K, and then you can also calculate your damping constant. Okay, so these are all the overview of what we have covered before. We talk about undamped where zeta is 0. We have underdamped system less than 1. Critical system equals to 1. Overdamped is more than 1. So it's easy. Normally we memorize. Over means more than 1. Easy. Under means less than 1. And then in between you have the critically damped condition. Alright, so I guess that's all for this lecture. So I hope you take a look at the quiz and the example. Okay, thank you very much. Bye.